Okay. Now, another thing I want to tell you here is that if you see a Z transformation in this format, okay, in this format, right, take the Z transform of this block, right, you can think it like sampling a function, for example, if it is a step function, you know how to write samples. Okay, it is USKT or just UKT. U is the unit step, but now you don't have the value at all times, right? But at specific KT times. So you just write U of KT. All right. So you write it down in the time domain directly, sampled version, 1/s. Then it is easier for you to convert it into the Z transform. So 1/s plus a also, you know, in Laplace domain, you have 1/s plus a whenever you have e to the at, right? This is from the Laplace table. So anybody who knows about Laplace, when they see 1/s plus a, they know that the time function is e to the at. Now, if t is not continuous, right, you just can't write t, but you have to write it as kt. Then you replace t from kt, just that. Okay, so this way what you do is you get the Laplace and then you mentally work it out into time domain, continuous time, and then change t to kt. Right, now here both of these functions are time functions and they are discrete time now. Okay, follow this procedure. Then in Z domain, right, UKT, the sampled unit step, okay, if you refer to the table, it is Z over Z minus 1, and this is sampled exponential function, right? In the Z table, it is Z over Z minus e to the minus at, right? And after that, you multiply, this one is 1 minus 1 over Z. You can write it this way also. Then when you multiply this, expand this entire bracket with Z minus 1 over Z, you will get to this one, 1 minus Z minus 1 over this thing, right? So once you simplify, it becomes like this. So what is it? It is the zero-order Hall equivalent of the plant. So the plant will not behave as it used to behave, right, in the continuous world. Now you have modified it with a zero-order Hall. So its behavior is slightly different. And also, please take a note of this one, SysD. This is a system in discrete time. C to D, SysC, continuous time plant. Then TS is the time sampling interval. And then zero-order Hall. So look at this command structure in MATLAB. You can self-study that one. In single command, you can convert, you can get the zero-order Hall equivalent of the plant. Okay. Give it a little time and practice yourself in MATLAB. And also there are advanced options here, right? When you do this conversion, we have studied the zero-order Hall conversion. But if it is not zero-order Hall, but something different, let's say, for example, Tustin, as I said to you, right, you don't need to stick to the zero-order Hall always. There are other approximation techniques as well, regression analysis, etc. Different techniques, right? You can take any one of them. So MATLAB provides couple like Tustin, for example, is very famous. You can replace zero-order Hall with Tustin if you want, right? Then you get yet another different discrete transfer function. The other thing, pre-warping, point to, and all these things we will look at later, not right now. Okay. Let's take a little break and about another 5 minutes, and I'll see you after the break. All right, welcome back. I thought of working out another example with you. I feel you lack experience working in this area. What about this one? If the first order plant, the one we worked out, right, before the break, is controlled by a proportional controller, right? Okay, the same plant, first order plant, and now you have a proportional controller to control it. Determine the stable range of the proportional gain for A equals 10, because there was an A there, right? That is the pole of the plant, A, and 20 hertz sampling. So assuming you are getting the samples at 20 hertz, right? What is the range for the proportional gain, the stable range, right? That is the design problem. So let me show you how we tackle this problem. Right. So watch very carefully and try to get familiar with what we are doing here, right? Otherwise, this will be a very annoying experience to all of you, especially the first one, just before the break. You're not able to work that out. Right. So this is the plant we are having right now. Okay, so you need to get going, even though you don't have any idea of what the final design would be, right? Take your first step. That is very, very important, right? Do not hold it back. Take your first step. Just draw it. Then something will pop up and you might see something, right? Way to get going. So we have the plant here, P is it? We have already developed that, right? Zero order hole equivalent circuit, equivalent of the zero order hole plant, okay? Or the other way around, zero order equivalent of the continuous time plant. That we have already, we built it. And now we have this KP in front of that because it said the controller is just a proportional controller. So it's just a gain, KP. Right now, you know that there's nothing much beyond what we already discussed before the break, just a constant. So when you have a constant in front of the plant, right, you don't have to derive the model again. It's just a constant. Okay, so therefore there are changes like that, right? Apparently there's nothing that is going to change because of the controller. Okay, because the controller is a constant. So if you do not take the first step, you will never see the opportunity, right? Opportunity is just covered with a screen. So you need to break that screen and go beyond that, then you will see the opportunity, right? So If you write down the closed loop transfer function of this one, right? It is if you bundle this whole thing as the forward loop, this one over 1 plus k p times pz, right? So that is your closed loop transfer function, and what comes in the denominator is the characteristic equation that we have already done, okay, in the past. So if you just check the characteristic equation, that is 1 plus kp constant times pz, you will write it like that, because pz is already known, 1 minus e to the minus at over z minus e to the at, that we have derived earlier, right? And then you simplify it. I'm not going through every step. Then you are in a position to get the closed loop poles, right? Closed loop poles. So that Z is equal to e to the minus at minus kp times 1 minus e to the minus at. So this is your closed loop poles, and they are in discrete domain, Z domain, okay? Now, we want to find out the stable gain range for the gain, right? In discrete time, we know that the plant is stable if you have the poles, right? All of them inside the unit circle, right? If the poles are outside the unit circle, the plant is unstable. So therefore, your pole here is a single pole case, right? This pole has to be inside the unit circle, this one, okay, for the plant to be stable. So then we write, if you look at the magnitude of the plant, right, of the pole rather, this is a complex number generally, right? But in this particular case, it all become real because a single pole. Single pole case cannot be imaginary, because you know every time you have complex poles, they come in pairs, 2, 4, 8, like that. A first order system is always non-oscillatory, so therefore the imaginary part is 0. So this is just a point on the x-axis, so it should be to the right of this point and to the left of that point. So we write -1, right, less than or equal to z, or less than or equal to 1. So you have two constraints on left side and right side, and this is your pole, right? You work out this way on the left hand side, right? Kp should be less than this thing, and on the right hand side, Kp has to be greater than this value. Right? This is a negative value, this is positive value. Okay. So we have two conditions now. For the plant to be stable, the closed loop plant to be stable. Now we put the numbers that we know, right? This plant pole is at -10, A is 10. And also when you discretize the plant, you use a sampler, right? About 20 Hertz sampler. So T, capital T, is sampling interval, which is 0.05. Now you can substitute these numbers for A and T, and then if you do that, you will eventually get this one, right? That Kp should be greater than 0.19, which is negative value, and it should be less than 4.08. So there's a range. There's a range. Okay. So any Kp within that range will make sure that the system is stable. Okay. So the plant is actually now sampled at 20 hertz. If you change the sampling interval to 30, 40, or 10, these numbers are going to change. These values 0.19 and 4.08, because these numbers are actually coming from T, A, etc. Okay, sampling interval is an inherent part of all these numbers. So what we understand here is that stability of a discrete plant, right, has something to do with sampling interval. Okay, so it's not a constant number like in continuous time case. Right, when you change the sampling interval, all the parameters of the plant are going to change. Now, for our own interest, if you want to look at the continuous time plant and see the stability, right, you can do that over here. Closed loop transfer function continuous time, it is just this, and once you derive it closed loop poles, it will be minus a 1 plus kp. This is something we have seen earlier also in the first semester, single pole case in the feedback loop. And it has to be on the negative half plane, right? So this minus a 1 plus kp, the whole thing should be greater than or equal to 0, right? This part has to be greater than or equal to 0. Then with the negative sign, the pole will be on the negative half plane. Okay, right. So when you do that, this is the result you get. Kp is greater than or equal to minus 0.9. So you can use any gain beyond 0.9. The plant will be stable if it is continuous. It is continuous. But in case of discretization, right, it's different altogether. You have to look at how fast you get the samples, and the sampling interval, say 0.05 second, you get these numbers. Okay, you have to stay below 4.08. Okay, can't go beyond that, and the system becomes unstable. Right. Any questions, please? Is everything clear to everyone? Okay. So then let's move on. I think you have some experience now. At least you can do a couple of things. One, after these exercises I did with you today, I safely assume that you can derive the discrete time plant model, right, for a zero order whole continuous time plant, right? So it's one single equation. You execute that equation. That is one thing. The second thing, if I ask you to design a feedback loop for a discrete time plant, right, you can do that and get the characteristic equation, which is a discrete time, and then analyze the stability. Right? At least these two things, extremely important. Okay, right. Then we'll continue our discussion that we started earlier, frequency response, right? What these blocks are actually doing in the frequency domain, okay, frequency domain. For that, we will look at the new components that we introduced. First of all, the zero to whole, okay, zero to whole circuit. What is it? So earlier we saw that the transfer function in continuous time domain, right, is this one for zero to whole. Have you got that? We gave it a impulse and we got the response. Of course, you know, if you give just impulse to the zero to whole, you get the step, just one step, one time sample, right? One step, and that's it. So if you know the pulse response of a block and you get the Z transform of the pulse response, it is the discrete time model of the block, okay, that we have figured out maybe last week. So this is the continuous time representation of the pulse response, right? Continuous time pulse response. You write it that way, right? Now for frequency analysis, we don't need to go to Z domain because the frequency analysis is entirely done in Laplace domain, right? So this is not a discussion with the Z transform, but Laplace. So we simply get the, because we want to get the transfer function, we need to use this one, zero to whole equivalent. Sorry, zero to whole plant model, right? Or the transfer function of the zero to whole. Now, this is one thing. The other thing I want you to know is that when we analyze transfer functions in terms of their frequency response, how they handle frequencies and all, we substitute j omega in place of s. You know that, no? So in undergrad also we did that. S equals j omega, which means is pure frequency response. You have the input sinusoidal waveform, which is not decaying or which is not increasing either. It is the sustained pure single frequency oscillation. Okay, so we do that if we, whenever we want to analyze a transfer function, a block, right, to figure out how frequencies undergo different changes as they move through the block. So now what we do here is that we replace S with j omega. Now we can see it over here. Zero the whole circuit, that block, right? S changes to j omega. And the right hand side, 1 over S becomes like 1 over j omega. 1 minus e to the minus ts becomes like this. And after that, we have a little bit of a mathematical manipulation here. This one is written as two terms here, but you can see when you multiply these two together, the two exponents add together, and it is the same exponent minus here plus here. So when you add them together, the exponent will be e to the, say, 0. So anything to the power 0 is 1, right? This is one way of writing 1, right, as two exponential terms. And this one, e to the minus tj omega, is also written in a very similar way, right? As half and half here. They're both negative, so they add together. So after that, you just simplify this one to e to the j omega t by 2 over omega, right? And you can see here the sine omega t by 2, right? Because you know e to the j theta minus e to the minus j theta over 2j is sine. That's another way of writing sine, okay? So sine omega t by 2 over omega. So now j is only in this exponent here, j omega t by 2. So this term will tell you about the phase, right? This j term, right? And the other terms will tell you about the magnitude. So they're both frequency dependent. Now we have some better idea of what the zeroed whole circuit is, right, in terms of frequency. Now, if you want to get the magnitude, how the magnitude of different frequencies change as the signal passes through the zeroed whole block, right? You need to get the magnitude of this one. So then it is from here it is t sine omega t2 over omega t2, right? Omega t by 2. So this e to the minus j omega t by 2 is the phase term. This is the phase term, right? So you don't take that one and take the other one's magnitude term. And the phase is e to the minus j omega t by 2. So you look at the constant here after j, omega t by 2, and it is negative. So negative omega t by 2 is the phase. And it's negative. Negative means loss. Okay. So I think we saw this earlier also. Every time you get a signal through a zeroed hole, you introduce t by 2 time delay. Now there you can see it very clear, t by 2. Okay, this is not a surprise, or this is not a significant derivation either, but very interesting because we manually saw the delay of t by 2, and the moment you multiply it with omega, you get it, you convert it to radians. This much of radians, okay, is lost for that particular frequency, and the phase loss is a function of frequency. So higher frequencies undergo higher losses. Higher the frequency, greater the losses, right? So this is the magnitude part, and it's very interesting to see the magnitude sine omega t or sine omega t over 2 over sine omega t over 2. So this is like sine theta over theta. It's a very famous function in mathematics, sinc function, sine over theta, or sine theta over theta. So now you can draw these two waveforms, these two graphs rather, Bode graphs for zeroed hole. When you do that, you will see this, right? You will see this. So what is it? The magnitude, right, will stay at 1, which means there's no attenuation. Um, um, so lower frequency signals, right? They all go from left to right without the magnitude undergoing any changes. The same magnitude, input magnitude is equal to output magnitude. Okay, no attenuation. But as you increase your frequency for higher frequencies, and this is 10 to the 0 means 1, right? 1 radians per second. And then you further go up, this is 0.5 omega s. That is omega s is actually uh, the sampling frequency. So this is half of that. This is half of that. Hold on a second. All right. So this is half of the sampling frequency. Let's say we have 20 hertz sampling. So when you go to about 10, so in terms of radians per second, right? Not hertz. So let's say you have how much? 120 hertz, 120 radians per second, let's say, right? 120 radians per second frequency, which is 20 hertz. Okay. Half of that, if you go to half of that, you will see a little attenuation. Little attenuation. So after that, you will see some serious drop in attenuation. And after that, it bounced back like that. But actually, this one is a bit confusing, this curve. In fact, this is going down. This whole thing is actually going down like that, right? Um, uh, so in a sync function, you can see that where you have all this frequency and amplitude together. So here we have broken it down and we see only uh, the magnitude going like that and bouncing back. So this is when you have 180 degree out of phase. You can see it over here. This is the phase, right? When you go to a 0.5, okay, half of the sampling, right, frequency. So you have this much of phase loss, right? And then phase loss can be 180 degrees, like over here, right, at a certain frequency. And after that, it's going beyond 180, but what we do here, we zero it and then keep going again. It's a slightly different illustration here. I think you got the idea. You got the idea. In a sinusoidal waveform, amplitude drops to the negative side and goes to the positive side. I like that. So this is that inverted to the positive side, right? All right. So the zero order whole circuit is a bit more complicated than you would have initially thought, right? You thought probably it takes the samples, that's it. But actually, it's doing a little more than that. It deteriorate the frequency spectrum, right? Now, if you design your system so that you stay here like that, this is half of the sampling frequency. The sampling frequency is something you can design arbitrarily, whether it is 20 or 200, is all your choice, right? If you look at the system bandwidth, okay, what sort of system is it? Are you dealing with your plant bandwidth? Let's say it is 10 hertz. Let's say it is 10 hertz. And if you set your sampling 10 times, if you set your sampling 10 times of that, okay, then when you get half of that, that is 5 times. This is that point. This is 5 times the bandwidth point, right? 5 times the bandwidth point. So 5 times the bandwidth point, you have a little attenuation. And the 5 times the bandwidth point, you have this much of phase loss. But 5 times the bandwidth means you don't have any signal in that range. You have the genuine signal up to your bandwidth. So therefore, you need to just look at somewhere over here, this part of the zero order whole body plot. Because this is your system frequencies are limited to this area. That is why you need to set your sampling interval sufficiently high, 10 times or more. Okay. Then these anomalies will not make any adverse effect in your plant because your frequencies are limited to this area. So there you don't have any magnitude change, attenuation, or any phase loss either. So this very simple design criterion, right, makes your life a lot easier without going through rigorous mathematics derivation. Simply it is set your sampling frequencies sufficiently high so that none of these anomalies, right, that you see on the body plot of zero order whole, right, will have a chance to deteriorate your signals. Any questions, please? Is everything clear to everyone? So let me ask. Dhananjay?
Yes, it's clear, but anyhow, let's say the the frequency,
Hmm.
we are like allowing it to be like multiples of something like let's say it's tens or twenties. Is
Hmm.
there a higher limit to that thing?
Yeah, of course, yes. Because, if you set very high sampling rate, obviously, you will not have any problem with your signals, right? They are not attenuated, they are not phase lagged. But the problem is, you are generating a lot of data, right? Let's say the amount of data you generate in 1 second doubles when you increase the frequency by a factor of 2. When you double the frequency, you deal with double the bit rate, right? And if you increase it three times bit rate, and then higher bit rate channels are required, right? Things become a bit more expensive, right? That is the only reason. And if you have sufficiently capable hardware to handle all this high frequency sampling and all that, you can exercise it without any problem. And the other thing is, once you achieve a certain amount of accuracy, you need not to look for any further accuracy, as I already explained before the break, right? You can figure out what sort of delay you can exercise. Say, for example, you have 45-degree phase margin, and you can go down to about 35, right? Without any harm. So, which means you have 10 degrees, right, as your phase loss. You are going to have a phase loss, right? You're going to have phase loss the moment you convert your continuous time into discrete time. Now, you can actually sacrifice 10 degrees. And over here, you can figure that out. What is that particular sampling frequency which will give me 10-degree phase loss, right, at that particular bandwidth frequency? You know your bandwidth frequency, right? What is the sampling rate that will give me 10-degree phase loss? If you said 0-degree phase loss, then you are in trouble. It will give you very high sampling rate. That is totally unnecessary because you can accommodate some phase loss. Remember, when we were doing this uh, back in semester 1, uh, we decided, okay, every plant we need to have about 45-degree phase margin, initial design, okay? That is why it is so important to have that much phase margin, because now in the second semester, when you convert into discrete format, right, you have to sacrifice some of that phase that you already retained in the discrete continuous time control design, right? Had you put it like 15 degrees in the first design, now you are in trouble because there's nothing much to be sacrificed, right? In your digital transformation. So you are in trouble. You need to have very high frequency sampler, which is very expensive. So if you design your system originally with 45-degree phase margin, you can safely sacrifice even 15 degrees, right? So you fix the point over here, 15 degree. Where is 15 degree? And what is the sampling frequency for that? And that is kind of safe, low end sampling frequency. All right. Any other questions? And is that clear to you, Dhananjay?
Yes, sir. That's clear.
Right. Sanjeev Kant, is it clear to you?
Yes, sir. It's great.
Right. Vitanasiri
Yes, sir.
and Jokshan.
Yes, sir.
Right. Vihangi. Pereira. Don't know what's happening with them. Tilanka.
Yes, sir. Clear.
Right. Okay, good. Fine. Right. Make sure you don't have any anything that is not clear to you, right? Because going forward with certain unknown blocks in the past is very, very frustrating, right? So it keeps adding stress to you, right? Because you don't know certain things, even though you solve sums, you don't know what it is. So it's no fun, right? So make sure you know everything, right? Now let us look at something like holistic design, and where this delay comes into action, right? And how we simulate the response because of this delay. This is going to end with an assignment. I'm going to give it to you. You have to work it out and submit me your answers, right? Okay, it starts off like this. You have a plant, second order plant, 1 over s plus 1 square, right? It's very simple. Uh, uh, Plant has 2 poles, minus 1. They coincide, something like that, right? And then you have the controller here, right? You close the loop. So when you do that, uh, you will see that in root locus design, I think you remember that, right? You have 2 poles and no zeros. So n minus m is 2 minus 0, right? Which is 2, right? To have 2 asymptotes, and you want to find out where they intersect, right? In fact, 2 asymptotes means one single line, right? So alpha, where they intersect or where they cross the x-axis, is summation of poles minus summation of zeros divided by n minus m, which is minus 1. Again, right over here. So when you increase your gain, right, what will happen is that one pole goes up, the other pole goes down. So this is all what we have already covered in semester 1, root locus. Now let's say we want to add a lead compensator to shift this asymptotes to the left to make it a little bit more stable. Okay, so a lead compensator is a 0 and a pole. You know that, right? So we put the 0 here. Let's say it's arbitrary design, and pole over here, right? When we do that, what will happen is that these 2 poles which were together here, right? One of these poles will go to 0 here, right? And it settle at this 0 this way, right? The other pole goes to the left, and there's a new pole coming from the compensator, which is over here, which will also move to the right. And these 2 guys will meet up somewhere here, and then one goes up, the other goes down. That's how it happens. Okay, so it's a new root locus because of this compensator. All right. Now with that, we have moved the root locus to the left, and system is a bit more stable now. So the control system will look like this: Ks over S plus P, and there's a feedback gain K, right? This is a feedback gain K. You want to calculate this K in order to bring these 2 poles, this one and this one, into a certain locations on the x-axis. So if you want it to be complex, you can do that as well. Okay, so all these things we have done pretty much. This K, you can adjust it if you want to keep the same gain without changing the forward gain, right? Keep the bandwidth intact. Right. So now we want to determine the lead compensator pole in order to locate the 2 poles simultaneously at -3 and -4. Let's say you want to locate the poles at -3 and -4. So for that, what we do is that we take the characteristic equation of the plant. If you look at this one, the plant, right? This is the forward loop, right? This is a forward loop, and the feedback gain is just k. So this is a forward loop over 1 plus k times forward loop. The closed loop transfer function, and then the denominator of that is the characteristic equation when you set it to 0. So it is 1 plus k times GC GP. This is the whole open loop transfer function, controller or compensator, and the plant, right? Everything is clear. So when you bring it down, say with this 1 to the right hand side, it becomes -1. It's a complex function. -1 means complex -1. So it has magnitude 1 and phase 180 degrees, right? So let's take the magnitude. Then you don't have this -1 because -1 comes with the phase, right? +1 is 0 phase, -1 is 180 degree phase, right? +1 is over here, -1 is over here. So then you can calculate your K as 1 over magnitude GC GP. If you get the magnitude of this one and the reciprocal of that, right, you can calculate K. That is the feedback gain, right? So this is the relationship between the poles and the gain, poles and the gain. So if you know the pole location, you can calculate the gain. If you know the gain, you can calculate the poles, vice versa, right? So now if you want to set your poles -3 and -4, you can use this equation, right? Once for s equals -3, s is the pole, -3, and second pole at -4, and then you equate them. They are equal to each other, right? With the same gain, you locate your pole, one at -3, the other one at -4. So when you bring it down further, you will see you get this equation, and finally your pole is to be located at 5.45. Okay, 5.45. So how do we set the pole at 5.45? So if you go back, you can see the pole over here. We don't know the pole location here, right? We have already set this 0 at the origin because this is only 1 degree of freedom equation. You can't have two unknowns or variables. Fix one of them at 0, that is 0. The pole, you have to fix it. So in order to achieve both poles, right, one at -3 and at the same time the other one at -4 with a single gain. This is not easily doable. With a single gain, you want to place the two poles at -3 and -4 simultaneously. So therefore, the pole has to be located in a particular point to allow that. Okay. So we have figured that out as 5.45. And after that, you can go to any of these gain equations, gain expressions here, and substitute P equals 5.45, right? And S equals -3, right, over here, or -4, it doesn't matter. Then you calculate K as 3.26. So this is simple design calculations anybody would do, right, in order to, when you design a lead compensator and set your feedback gains. Okay, right. So I just did that to help you improve your confidence, right? And also connect the content we are discussing here with things we did in the past. So now, if you want to continue this to a discrete controller or digital controller, right? We want to see what sort of errors are there. We want to simulate it before we do that. Okay. So one thing is the delay. Right. So let's say there is a sampler, right, which is operating at 10 hertz. It gets 10 samples every second, right? So which is 0.1 second delay. Now we want to simulate the plant with the compensator, with the feedback gain, right? Everything, and also with the delay. So without the delay, you can see it on MATLAB and you are happy about it. But if you introduce the delay, the sampler, and zero the whole, you want to see how much the duration goes further from this point, right? So for that, there is a little trick. We call this Paddy approximation, right? E to the minus TD over 2s time delay by 2 is actually the approximation, right? It goes like this: 1 minus TDS over 2 over 1 plus TDS over 2, or this way: S minus 2 over TD, S plus 2 over TD. So what is that? This is another block. This is another block transfer function which will approximate the delay, the effect of the delay, right? Now, there you don't have the S in the exponent like over here. This is the major problem, right, in discretization, because if you continue with the Laplace, S goes to the exponent and you are in trouble. That is why we have the Z transform also, right, to get rid of that. And now we have another approximation for the delay, e to the minus TD over 2 over S. This whole block can be represented like this. And if you know the delay, and if you want to simulate the plant with the delay, all what you need to do is to include this block into the plant in front of the plant, right? And simulate and see what you get. So if the time delay is, let's say, 0.1, this is in fact the entire sampling interval, not the time delay, right? Sampling interval 0.1 divided by 2, right? That is 0.05. So the entire block takes this form: minus S minus 40, S plus 40. So it's a pole zero block, one pole, 1 0, right? The pole is at minus 40, the zero is at plus 40. And you can see for the first time um, a block, right? With a zero and pole, and zero is on the right half plane. Right. So I'm going to give this as a homework, an exercise. I will write it down and upload to the Moodle. You can download the assignment and work it out and submit. Okay, I'll give you about 2 weeks to finish it off. And make sure you submit everything to the Moodle, right? Not email to me. So last semester, I think, or 2 semesters back, somebody has mistakenly emailed it to me, my Gmail, and I couldn't find it because I can't do that, right? That is why I ask everybody to submit assignments to the Moodle. And if you find any problems, you have to communicate quickly to me. Then I can extend the deadline for you to submit, right? Extensions can sometimes lead to some penalties of marks, but there won't be any other serious problem. And luckily, I got the email recovered, and it took a lot of time to figure that out. And it's totally not worth it, not worth the time and effort. Okay, so make sure you submit everything to the Moodle so that I can download the zip file to my computer and evaluate all these things very efficiently. Okay, right. So no email submissions whatsoever, right? It's everything has to be to the Moodle, right? So now this is your plant, right? Um, the pole of the compensate is 5.45, and what the feedback gain is 3.27. We calculated that, and also the time delay we introduce over here, because maybe this is the best place to introduce, right? You get Y, the response, and then the time delay block, and then it's over here, right? If you place this one somewhere else, right? You have to be careful whether this serves the purpose or not. Now, if you look at the pole zero plot, it'll look like this. You have the 0 at the origin. This is what we fix the 0 at. And then 2 poles at -1 is the original plant. And you have what? 5.45 minus. This is the pole of the compensator. That's also there. And then now you have two other poles over here, -40 and +40. This is for the pole 0. This is for the pole. Now see, your equivalent discrete time plant is much more complicated than the original plant. Okay, so that is why we need to simulate all these blocks, the delay and everything else, right? And see for ourselves how the response changes. So if you get reasonably good result, right, and you are happy about it, because when you discretize the plant, you will still get something closer to what you see over here, right? Because this is delay included. So you have confidence to discretize the plant. Right. So this sampling delay has been a little problem. So that's why this Paddy came up with various ways to represent modeling, represent different delay models, right? So there you can see very clearly the best way to model the plant and the controller. So let's say you have a plant PS and you have the controller CS. Okay. And then what you do is, as I already explained, you convert the CS into CEZ. CS into CEZ, right? But PS stay the same. But later, we added a zeroed hole equivalent of this one. And now we don't need to use PS. We can use the equivalent model of the plant, right? Then that'll give you a better result. But the problem is then the CS is not matching with that plant, right? Because CS has been designed based on PS. Now with the zeroed hole and all, PS is going to change into something. Therefore, your controller has to be designed based on that model, the equivalent model, discrete model. And you get the point, right? Therefore, my initial advocate to you, okay, you go ahead and design your continuous time controller with all the tools in continuous time, and then transform the continuous time controller into discrete time. It's not very accurate. Now you know that. Okay. So this is the process. Right. Now you understand that you will be better off if you take not PS, but the equivalent transfer function of PS, including to it the zeroed hole, right, into account, and design the controller with that. Okay. Or else you can do it like that. You put e to the TS in front of PS. So this is the time delay version of PS. Now you design your controller based on the time delayed version of the plant. This is also very good. Okay. Now here you can do this without ever going to discrete domain. Okay. Without ever going to Z domain, you can do this whole thing in S domain, Laplace domain itself. If you have a representation for e to the minus ts. Okay. Now make sure everything is you place in proper position, right? So now we say this, design the controller based on the delayed plant model, e to the minus ts times ps. So that controller will be different from this controller, right? because this one doesn't know anything about the delay the plant is undergoing, but this controller knows that the response is delayed by a certain time, so that I need to take proper action. Okay. So all what we need now is some approximation to e to the minus ts, because e to the minus ts cannot be taken forward, right? And that is why the Paddy approximation comes in over here, e to the minus ts. This is the first order Paddy approximation, the second order Paddy approximation, so on. But we don't have to look at all these things. First order is sufficient. Okay, and more than the Paddy approximation, what I want you to understand is the logic here, how we develop the techniques, right? Step by step, and increasing the accuracy every step. So if you know the delay, you can put it over here, and also n is the order of the Paddy approximation. If you go to the first order approximation, n equals 1, right? And this is the generic Laplace transfer function or block that you can easily include into the plant. Right. So I want to do the deadbeat control, which is the discrete control system, very famous, but I don't have time for that today. I will take that next week, deadbeat control. And I will prepare this assignment, I think the first assignment, and upload to the Moodle so that you can download it and work it out within the next 2 weeks. Right. So is everything clear up to now? The answer? Is everything clear to you?
Yes, sir.
Right. Chamira?
Yes, sir, but we need to watch this again.
Oh, yeah. If you have any concern, anything which is not very clear, and if you are sure about what is not known, why don't you ask now? We have about 10 minutes more.
This thing overall, it's clear, sir.
Right.
But it's better to ask again.
All right. Okay. Then who else? Vitana City? And Vihangi? And not there? Tilanka? Jokshan?
Yes, sir.
All right. So make sure you take some good time to arrange all these things that you learned, right, up to now.
Clear, sir.
Particularly when you convert a plant from continuous time to discrete time, right? There are important things that you need to do. You want to simulate the plant and see for yourself if the discrete version is also performing in a reasonable manner, right? And for that, you need to change your controller and discretize it. And also you have to change your plant into their discrete model. And if you zero the hole, you put that block in here, right? And then get that one. And you can go ahead and design your discrete controller. And also delay comes in, right? So if you do not want to go to discrete world and see for yourself how the delay affects the response, what you want to do is put a delay block in front of the transfer function or the sensor, right? And then simulate the whole thing, right? To figure out what sort of deteriorations are happening. There can be slight deteriorations, but then you change your sampling interval in a range and see for what sampling intervals you get better performance and for what you are not going to get any useful response. So some time that you spend on this one, on simulation, all that is extremely important for you to actually develop the skills. And remember, the control is not something that you just write on paper, right? And it's a lot of simulations in MATLAB. I know there's no chance for you to go and practice a lot of things, right? There's no such need seriously, unless you are actually doing it in your regular daily work. But you can do quite a lot in MATLAB, simulation and everything. You can generate a lot of knowledge. You can assemble your knowledge pieces together entirely on MATLAB. So I'm asking you to do certain coding in assignments and all that. You can do that, but in addition to that, right, make it a habit, right? If you have a certain problem, why don't you go to MATLAB and code it and keep your codes in a repository, right, and develop gradually. That's how people do in industry. They have coded certain things and they keep them, and whenever they want to reuse it, they can reuse it, right? So new problems they can handle quite easily because you have a history of an code base that you can make use of, right, at any time. All right, with that, I want to wind up the session today. Yeah, so I'll see you next week. Have a good evening.
Thank you, sir.
Thank you.
Thank you.